Good morning, everyone. Thanks for waking up early and coming to Fluids to Vortex Electric Boogaloo. I will be your host, Ted Kim from Pixar Animation Studios, and we have 4 really interesting papers. And we're going to start off with water surface wavelets, and the presenter will be Stefan Jeschke.
Okay, thanks. So good morning, everyone. Thanks for showing up so early here. So let's begin with the fast-forward teaser to show you where we are going with this work. So here you see a detailed wave animation. And if we throw in an object, then it causes dynamic ripples, so it interacts with this water. And this also scales well to these 1,000 barrels here. We also get reflecting boundaries, as you can see here for this boat wake. And it even scales better to like 1,000 boats here. And all this was recorded on this laptop at 60 frames per second. Okay, so before we start, let's have a look at the state of the art in large-scale water animation. That gives us a primer of what's coming afterwards. In doing so, we're going to focus on the visual detail, where the scene size that I call scalability here on the x-axis, and the environment interactions like reflecting boundaries, dynamic wave emissions, and so on here on the y-axis. So procedural waves provide really kind of an unlimited visual detail. As you can see here on the right, they're really detailed waves, but unfortunately they provide 0 environment interactions. So the boat on the right doesn't emit any waves, and they do not reflect from the island boundaries and so on. However, this is still kind of the state of the art in today's computer games. So for example, NVIDIA's Waveworks is one example. Often it's augmented with a few ripples or something, but that's pretty much it. In a talk paper from 2015, we improved this a little bit by pre-computing a wave path in a pre-process. And this way we got like boundary interactions and refractions and so on. But being all this pre-computed, of course, something like boat waves and other dynamic effects are not possible this way. So on the other side of the spectrum, there are numerical Eulerian simulations. So these provide really unlimited environment interactions, but unfortunately the visual detail is pretty limited. So for example, here on the right, the smallest achievable details are 2-meter wavelengths. That is just limited by the grid resolution here. So that's not really detailed, but you get boundary reflections and all that stuff. So another line of research are so-called Lagrangian approaches, started in 2007 with so-called wave particles. So they provide quite a few environment interactions like reflections and these dynamic ripples emitted from the boats here, and also some visual details. So you get locally higher res details than with Eulerian simulations. Last year we had a SIGGRAPH paper that improved this, where you get even more interactions and more details. But ultimately, the number of particles can quickly become prohibitive if you have a scene like these 1,000 boats that we saw before. So in this work, we're trying to bridge this gap. So getting all the nice environment interactions from the Eulerian simulation, and at the same time getting all the details from the procedural models. So let's first start with some theory. So here you see the basic procedural wave model, where basically the water height eta at location x and time t is just an integral over all wave vectors k, and each component is the product of an amplitude function a and a cosine that is driven by some phase function that basically encodes the dispersion relation of water waves, so relating wave length to its speed. Now, the main idea of this work is to extend the amplitude function using the Gabor wavelet transform to now also depend on spatial location and time. So this looks rather trivial here, but deriving this from physics is not trivial at all. So I don't want to bore you with the details here, but refer to the paper. So basically the idea now is to use an Eulerian simulation to advect A, and the details are still coming from the cosine term, sort of. So this forms the theoretical foundation of our method, but for didactic reasons, we're going to switch over to a discrete version of this. So starting with this, after changing to polar coordinates and doing a discretization using the Galerkin method, we end up with this double sum here, which simply sums over all wave directions d and wavelength L. And again, we have our amplitude function and the cosine that's driven by a phase function, which is pretty much the same as you see on top, but k now divided into wave direction and wavelength. So this version is more intuitive the most, so in the remainder of this talk, we're going to work with this version here. So the first step is to add spatial dependence to the amplitude function. So basically, this is the basic procedural wave model where you can see that A just depends on the wave direction theta and wavelength lambda, right? So for example, we can model A by just interpolating a few sample directions. Each is indicated here by a small black arrow. And basically, this basically globally amplifies waves running in certain directions. So this way you can model global wind waves or ocean swell or things like that. Now, the first step is to extend the amplitude function to now also depend on spatial location x. So for this, we use a spatial grid that stores these directional samples at each grid cell. So basically, this means the interpolation now happens over space and directions. So in all examples I'm going to show, we use a 4K by 4K grid and 16 directional samples per grid cell. So to illustrate this idea, we developed a tool that we call wave painting. So here a user directly paints these amplitude coefficients directly on the grid. So the first brush is a unidirectional brush, so that increases amplitudes in all directions. By contrast, the directional brush increases the amplitudes in the direction of the brush drag, so as indicated here by this arrow shape. So you can model pretty complicated wave flows in this way. So for example, this double swirl that would hardly appear in nature, but notice there's not really an artifact you can point to. So here's another example. Here we see an ocean and with islands from the top. And the common procedural waves ignore these island boundaries. But if we switch over to our model, you see that the waves close to boundaries align with the boundary. So here we just use the procedural way to, based on boundary proximity and boundary normals to define this behavior. So this basically shows that you can really play with the amplitude function depending on your application. So it's a pretty open space that you are free to play in. So the next step is to also add time dependence, because so far all the simulations were quasi-static, meaning they cannot represent time-dependent events like boat wakes and so on. So we're going to lift this now. Coming back to our spatial grid that stores the directional amplitudes, the idea is to extend the amplitude function by time. And the way we're going to implement this is we just use a PDE solver that advects the amplitudes on an Eulerian grid. So basically, during this advection, essentially what happens is that the amplitudes get just transported with group speed. So, which is exactly the speed of wave energy. So we derive this, this is a nice theoretical result that we derive in the paper. So in practice, we solved this transport equation with a common unconditionally stable semi-Lagrangian advection from previous work. And we also add reflecting boundary conditions for obstacles and transmitting boundary conditions at the domain limits. Again, working at the same resolution as before. So to illustrate how the solver works in practice, here on the left, you can see the amplitude data. This is this blue function on the grid. And compared to the right, there you can see that the amplitude values are it's really a smooth function compared to the wave heights on the right? So we get much better CFL and Nyquist limits on the amplitude function. So this is the reason why we get away with this relatively coarse grid and still get all the details. We also provide some basic object versus fluid coupling. So solids and water exchange energy via buoyancy and the amplitude simulation grid. So again, details are in the paper. Another concept I'm going to present is a multiscale simulation. So far, we worked with a single simulation grid that worked on all the wavelengths, so from really small one to really big ones, right? Now the idea is to run multiple separate wave simulations, each acting on a different scale, so on a different wavelength, as indicated here on the left. So the final wave displacement is then just a superposition of all these individual simulations. So, okay, what does this buy us in practice? So here's an example. This is a single scale from a boat wake, and you notice that the waves are equally distributed within this wake. So from left to right, there are small and big waves. But this is actually not what really happens in nature. It's happening something closer to this here, where I used 4 scales, so where the long waves outrun the small ones. Because the long ones now get a different group speed than the short ones here on the left. So this is closer to what happens in nature. So as a last concept, I'm going to present so-called profile buffers. So they form sort of the technological basis for this work. So that makes it actually fast. So coming back to our current wave model or wave height equation. So for realistic water, one has to accumulate several thousands of these waves. So that's pretty expensive. And that's why it's usually done using an IFFT on 2D textures and tile these textures over space. You can also add horizontal motion to get so-called toroidal waves or Gerstner or Biesel waves. I don't want to get into detail here, but I want to note that all this also carries over to the model I'm going to present now. So let's have a look at a single wave direction here. So essentially keeping D fixed in this. So we notice that all the locations along the red line compute precisely the same inner sum in this example, so as indicated above. Now, the idea is to pre-compute this wave height into what we call a profile buffer, that is simply a 1D texture that happens in every frame. And this profile buffer is then aligned in the scene and tiled along the wave direction. So now each spatial position now just projects into this alignment and reads the respective texture value. So this essentially replaces the whole inner sum above by a single texture read. So we can reuse this profile buffer for a number of wave directions, and this gives us this nice ocean here. So this assumes some separability of the amplitude function, and in the paper we talk about why this makes sense or why this is reasonable to assume. So in this case, the profile buffer gave us a speed of more than 2 orders of magnitude. So this is actually the key why the whole thing is running interactively. A valid question is to ask is, okay, how many directions do we need? So if you don't use enough directions, as seen here on the left, you see these streaking artifacts. This is simply because there's not enough variation in the ocean. But starting from about 40 directions on, these artifacts are gone, and yeah, you get this nice ocean here. So now I'm going to present a demo. Hopefully it works. So this basically runs on this laptop now at about 60 frames per second. And you see, you really get a lot of boats here. It's 1,000 boats. And we can also go close and get all the details, like here, these waves. And so what the simulation sees is basically it works on this grid here. And we also have a visualization of the data. The color indicates just the direction of travel of the wave energy or wave amplitude here, right? So you can see that this is basically what the simulation sees. What you can also do is you can toss in an object, like so. So what the simulation sees here is just marching out amplitudes. You can also toss in more, or even more. So these are 1,000 barrels here. And there's no drop in frame rate whatsoever. So in every frame we compute precisely the same thing here. We also get reflecting boundaries. Let me see if I find a place where we can see this. So maybe here a little bit. So here there was a boat and now it's reflecting off this boundary. Okay. So here's a breakdown of the performance and the memory requirements. The takeaway message is basically that the rendering, including evaluating the wave height, is pretty cheap. So in the example you just saw, for 2 times 120 directions, so for the foreground waves like boat waves and so on, and the background waves, we take just 4 milliseconds. So, but this is a rather academic setup. So in practice you can make that even much faster. What is a cost factor is the simulation grid. So we saw a 4K by 4K grid now that takes 8 milliseconds. But if you reduce the grid size, then it gets increasingly faster, and the memory also goes down. But of course you have to pay a price for this, right? So, and to illustrate what happens if we reduce the grid size, here's a raindrop example where on the lower right I showed the grid this is running on. This looks kind of okay. But if I increase the grid cell size, you see that the initial impacts rather become little patches here, because we cannot simulate anything that is smaller than the grid size, or grid cell size, actually, right? So, and if I further make them bigger, then you see now it looks rather like patches. So this is clearly the way it works here. So in terms of future work, another limitation of this is that we do not have explicit control over wave phase. So for example, you can see on the left that there is no perfect circular ripple, so there's no wave crest that really runs in a circle. This is because what we actually basically do is we blend different wave simulations running in different directions. So at the boundaries, this has an equal effect that the incoming wave in principle has nothing to do with the outcoming wave. We are just blending different wave directions here. But we are not very good at detecting this in practice, so that's why it looks kind of convincing. Similarly, boat waves, if you really want to model the Kelvin waves, then they rely on a complex superposition of many different waves, and therefore you also need phase control, which we cannot have. So it looks okay, but it's far from the right answer here. So what would also be interesting is to look into depth-dependent effects like this wave shoaling here on the left, and of course nonlinear effects like breaking waves to being able to model a large beach scene or something like that. So far, what I was talking about here is all linear wave theory, so this is far from getting things like this, right? So in summary, the surface wavelets provide a transition from simulating wave height to simulating directional wave amplitudes, which buys us largely improved CFL conditions and Nyquist limits. We get nice reflection, dispersion, diffraction, and dissipation effects handled. And on a practical side, so for computer games, a good thing is that this has a constant computational load. So there's no varying number of packets or particles or whatsoever. The implementation is rather simple. It's essentially two shaders. So we also provide a CPU source code, and you can also download the GPU binary from this demo and play yourself. So that's on our website. And we also provide a separate document detailing all the implementation details that we used in our implementation. So you get a really good starting point reproducing this. This concludes my talk. Thanks for your attention, and happy to answer questions.
So I think we have time for a question. If you could state your name and affiliation before you state, then that would be great. Yes?
Nelson Max, University of California, Davis. There was something I didn't understand about your profile texture speed up, because this amplitude that you grouped into this big sum was position dependent. So how can this 1D texture handle that?
Yeah, that's right, yeah. That's true. I was a little sloppy in that one for didactic reasons. You're right. The way I presented it here, it looked like it would depend on position, but the idea there is to factor out part of the amplitude to put it in front of the inner sum. So all that part that depends on spatial location can be put in front of the inner sum. And what actually happens is, maybe I go to that slide. So what I'm computing is the inner sum here. Here we go. So here.
It's not showing up on the screen.
Oh, sorry. Here we go. All right. So basically, so part of this amplitude function that depends on x, and all, basically t is then factored in because we repeat it in every frame. But the part that depends on x can be put in front of the inner sum here. And what happens is basically, imagine that a is just a value that depends on the wavelength here, and this is what we compute into the profile buffer. So it's kind of a standard wave spectrum that we compute into the profile buffer, and this we just increase or decrease with a factor that is in front of the sum. So this is the longest story for this, yeah. Yeah, but you're perfectly right. The way it's presented here, it's a little misleading, yeah.
All right, so unfortunately, I think we have to keep moving, but all the speakers will be up in front for further discussion after this session. So let's thank the speaker again.
Hello.
Can people in back hear okay? Can you give a thumbs up or down? Okay.
Thank you.
All right. Our next paper is tempoGAN, a temporally coherent volumetric GAN for super resolution fluid flow, and it will be presented by Rachel Chu and by Zhu Se.
Thank you very much for the introduction. Good morning, everyone. Let's start. At the beginning, I would like to locate our project into the big picture of research. Machine learning is a really exciting topic now, and people all know that AlphaGo has won human again and again in many areas, including image recognition, segmentation, and even generation. Machine learning methods are becoming state of the art. So people may ask, how about physics? Can neural networks learn the physical laws behind physical phenomena? This is a very interesting direction, but there is relatively fewer related work so far. Our tempoGAN is focusing in this direction. Specifically, we focus on fluid simulations. To our knowledge, tempoGAN is the first approach to synthesize four-dimensional physics fields with neural networks. Here is an example showing our goal. In fluid simulation, a low-resolution scene is usually fast to simulate, such as this 2D plume scene. If we increase the resolution from 128 square to 512 square, which is 4 times higher, we can see that the results are much more detailed and looks more realistic. However, the computational time is increasing superlinearly. So, the goal of our project is to infer this high-resolution configuration from the low-resolution data. Although not many, there are some related work using machine learning methods in fluid simulations, such as these 2 SIGGRAPH papers using regression forests and convolutional neural networks, respectively. In most related works, traditional trackings are still used, while our method is a generative model that purely relies on the trained network. At the same time as a super-resolution task, image super-resolution methods are also very relevant. In this area, generative adversarial networks show great power in adding realistic spatial details, and ResNet, with its residual learning strategy, also surpasses many other network structures. Compared to the previous works, our work has the following main contributions. First, we propose to use a novel temporal discriminator, which results in better temporal coherence. By using a discriminator-based feature loss, we find it makes the network generates better spatial details. At last but not least, we found that by using velocity as input as well, it makes the network easier to learn the physics behind. At the same time, it also allows for results modification. Later on, we will go into these highlight points one by one in detail. So here comes the temporal discriminator part. At first, we start from a standard GAN structure on our volumetric smoke data. Here, the X is a low-resolution density field, which could be in 2D or 3D, and our generator takes X as input and generate a high-resolution density field, GX. The goal is to have something that is very similar to the ground truth density field in high resolution, Y. Instead of using an L2 loss or other fixed losses, GAN project found that to train another network, a discriminator, to learn the loss function and to supervise the generator is a good way. So, during our training, the discriminator tried to identify the ground truth data Y as realistic, which is 1, and also at the same time it tries to mark the generated one as fake, which is 0. Here we use the standard binary cross entropy loss to train our discriminator. And on the other hand, the generator is trained to fool the discriminator, trying to be marked as 1. And we also use the standard adversarial loss there. So in such a standard GAN structure, the generator will be required to generate realistic spatial details that are very close to the ground truth state Y. So we can take a look of the result using such a standard GAN. On the left, we can see that the generated density field still flicks a lot. And if we take the time derivatives on the right, we can see that it is very strong and very noisy. Okay, so based on such a standard GAN structure, our task is to solve the temporal coherence problem, which means that we should have some kind of constraints between the adjacent generated frames. So now let's give 3 adjacent low-resolution density fields to the generator one by one. And then the generated results are also coherent. Because of fluid motion, those frames are different, and to compare them directly would be hard. However, we have the velocity field, and we can advect them with the velocity field. So now, the A stands for the advection step, and sometimes it is also called as the warp operation. And the frames in the circles are the advected warped frames. Here we warp the previous frame forward and the next frame backward, and in this way, these frames are better aligned. So how can we constrain the difference between these frames? If we use an L2 loss there, we can get a suboptimal solution, because this L2 loss will try to minimize the difference between this frame as much as possible. However, we know that even for the ground truth state Y, if we warp them with the low resolution velocity field, in the advected frames, they still contain some high frequency differences. So to overall minimize everything to 0 is not the optimal. Instead, we propose to use a temporal discriminator. So now, we still use the standard GAN losses, but now the data is not single frame data anymore. We train on the warped frames. And in the ground truth warped frames, they contain some reasonable differences. So the discriminator will learn how much difference is desired. In this way, it can supervise the generated results to contain similar amount of difference. So in this way, our generator is required to learn some kind of temporal coherence and keep this kind of temporal constraints in its results. Note that although our temporal discriminator is now trained with a sequence of input, our generator still works independently on every frame one by one, which makes our method frame parallelizable. Now we can compare the results between two different temporal losses. If we use the L2 temporal loss on the left, we can see that the derivative is still strong and noisy, and while using the temporal discriminator on the right, it is much clearer and smoother, and it shows the outline of the smoke, which indicates reasonable smoke motion. We can also compare the density field. Again, the tempoGAN achieves coherent and realistic results. From here, we can conclude that compared to a L2 temporal loss, temporal discriminator can represent better temporal constraints. We also have some examples in 3D. Here, the input is a simple 3D plume scene in low resolution, and the target is a ground truth, which has a 4 times higher resolution, and our tempoGAN result is in the middle. Again, you can see that from the blurry input, our tempoGAN achieves highly detailed results. In some part, we even have more details compared to our target, and at the same time, it is very tempo coherent. We can take a look of the tempoGAN result once again on the left, and now compare to a good standard GAN, but with no temporal discriminator. From here, we can see that tempoGAN achieves a clear improvement on the temporal coherence. So now that's about the temporal discriminator. How can our method achieve even more details compared to the target? The answer lies in the other two contributions, which will be explained by you.
Hello, I'm Yu. So I will introduce the other parts in the list. All right, let's go back to our overview. Richard just introduced the most part about the discriminator, so I will introduce more about the generator part as the next step. So according to this structure, we can summarize the loss function for our generator. At first, there are two terms come from the adversarial loss term come from the two discriminators. We train our generator in this way to fool the discriminators. We also add the L1 loss here to restrict the error of the outputs. And then we also add the feature space loss term here. So now I want to explain what is this feature space loss term. All right, let's focus on this term. As we know, what the discriminator does actually is the classification. So features of the inputs would be extracted by the discriminator layer by layer. For example, if we input a generated results, those features would be extracted the same. If we input a real date, those features also would be extracted. So we can use the feature space loss term to calculate the distance between the generated result and the reference. And we can control the distance by using different factors lambda. All right, now I also want to use some intuitive way to introduce the relationship between the GAN loss, L1 loss, and the feature space loss term with different factor lambda. At first, imagine there are three very strong boys, GAN loss, L1 loss, and the feature space loss. And now I want to use this coordinate, high and low frequent details to represent the detailed information in our results. Let's assume that there is a grand truth. All right, at first, let's assume that the feature space loss term factor lambda f are 0, which means there is no feature space loss term, only the GAN loss and the L1 loss, which push the result go to the direction of the grand truth. So this is the situation. So as a result, our result would be located around the grand truth. So let's regard this as a baseline. Then, if the factor lambda f are positive numbers, at first the GAN loss and the L1 loss are still the same. But if we use a positive lambda f, which means this term will push the model to decrease the feature space difference between the generated result and the reference. So this is the situation. So as a result, our result would be closer to the ground truth if we compare with the baseline. On the other hand, we also tried negative lambda f factors. At first, the GAN loss and the L1 loss are still the same. But if we use a negative factor lambda f, this is not very intuitive, because with the restriction of GAN loss and L1 loss, our results should be closer to the ground truth. But if we use both negative lambda f, so which means this term will push the model to increase the difference between the generated results and the reference. So just like this. But it is still possible for those three terms to go to a balanced state. So for example, it's also possible for the whole optimization process go to optimal point where the low-frequent details are quite similar with the ground truth. However, there are more different high-frequent details. So this is the situation. So compared with the baseline, there might be more details, more high-frequent details in our results. So let's check some test results. In this slide, we compared the positive lambda and zero lambda. If we focus on the middle part of the images, we can find the details are closer to the reference if we use a positive lambda. And in this slide, we compare the result of negative lambda and zero lambda. Still in the middle part of the images, we can find there are much more details if we use the negative factors. So overall, we can choose different factors according to our applications. All right, let's go back to the list. Actually, our structure is a very general structure. Here, we used density and velocity as the input. So for the next step, I want to explain why we choose the density and the velocity as a input. Because for super resolution problems in non-physics field, such as image super resolution, if we want to output high resolution images, we only need to input the low resolution images. But in physics field, we know that there are some potential relationship between the low resolution density, high resolution density, and some other parameters such as the velocity, verticity, and so on. And they are very easy to get during the simulation. So if we add them into the input set, it will be easier for the neural network to learn those relationships. This is the test results during the training process, and we compared the result with different input parameters. Let's check the results. It's very clear that if we use both the density and the velocity as the inputs, our training process converges faster and generates sharper results. All right, as I mentioned, our neural network built an approximate relationship between the density and the velocity. So if we fix the low resolution density input and modified our low resolution velocity input, so we can get different kind of high resolution density output, which means we can achieve some kind of controlling of our result. This is for example, this is a test that we modified the velocity. In the left part, we increase the velocity to 2 times as large as the original velocity, and for the right part, we set the velocity to 0. Let's check the results. It's very clear that in the left part, there are much more details. However, in the right part, where we set the velocity to 0, there are much less details. This also indicates that our neural network successfully learned the relationship between the details and the velocity. All right, we just showed some 2D results to clarify our algorithm, so now I want to show more 3D results. the left part is the input and the right part is the output. Actually, we only use one low resolution frame to generate one high resolution frame. So actually, our algorithm is time independent for generation. Now, let's check it again. At the output of the tube and the most part of the smoke, the details are recovered very well and still temporally coherent. In this test, I also want to discuss the performance of our algorithm. I will list some comparisons between the tempoGAN and the normal simulation. At first, the time. tempoGAN costs nearly 3.9 minutes per frame, but for the normal simulation, it costs nearly a half hour per frame. And for the generation time, tempoGAN increases linearly, but for simulation, it usually increases superlinearly. And as I mentioned, our tempoGAN is time independent, but for simulation, it usually outputs a time-dependent sequence. All right, there's another test that we used the obstacle. Actually, we did not put any obstacle data in our training data set, but it still performs very good here. Let's check the results. Still, the left part is the input and the right part is the output. We can find the details recovered very well and still temporally coherent. Let's check it again. The resolution is very huge here and it still performs very efficiently. And if we focus on the interaction between the smoke and the wall, actually there is no smoke go through the wall. All right, I just showed some very beautiful results, but actually there are still some limitations. For example, we fixed our upscale factor at 4, so in the future we also want to try even larger upscale factors or even multiple upscale factors. And the sad thing is that the training time for the 3D part is still very long. It took nearly 9 days for the whole training process. And currently, we just tried the buoyant smoke just like this. So in the future, we also want to try some other data set like the liquid, obstacle state set, and maybe some other physics problems, because in most of the physics field, the temporal information are very important. So all of our data are generated by MANIFlow, and our source code is available here. Thank you.
All right, we have time for questions. Again, please go to the mics, and if you could say your name and affiliation, that would be great.
Hi, my name is Yuping Zhang from University of Maryland, Baltimore County. I have a question. So you said your upscale is +4 right now. What's forbidden in going up?
You mean using larger upscale factors?
Yeah.
Actually, we currently just tried some tests for using upscale factor 4. So in the future, we also want to try larger factors.
So did you try more than 4 and the result doesn't look good?
It's still we are just still doing some testing in that direction. Yeah. Thanks.
So I have a question. So with a lot of these machine learning algorithms, it works well within a certain set, and then it sort of starts to break as you go outside the set. Can you give us an idea of like, does it break gracefully, or does it just fail all at once? What sort of happens when you go outside the training set?
You mean the training data set for our algorithm?
So usually, usually these algorithms fail at some point. Can you give us an idea of what it looks like when it fails?
I think maybe I can answer this question. So currently, our model is more trained for buoyancy field, and we show that in our house model that our smoke won't come across the walls. But if you add some active obstacles, I'm not pretty sure that if this model can handle the obstacle part correctly. So it might be some failure case because it's never seen in our training data. Yeah, but I think you can either train with more data, more general ways, and do some other improvements. So far we feel the low resolution still works good with kind of interactions, and then we kind of aiming for the super resolution task, which is relatively good for reasonable inputs.
Okay, thank you. Okay, go ahead.
Thanks for. Do I have time?
Yeah, you have time. Go ahead, please.
Thanks for this awesome work. I'm really impressed. Can you show me the performance page? I guess 3 page before, I guess.
Which one?
Yeah. Maybe one more, I guess.
Okay.
So linearly. Yeah. So you were. I think it's kind of trivial, but I just didn't get it. So the time increases linearly. Can you first explain this? So how would you expect your tempoGAN to scale with kind of size or resolution of the smoke you are trying to simulate? Thank you.
Okay. Actually, our tempoGAN algorithm is implemented with convolutional operations. So actually, if you increase the number of cells, for example, the resolution, so actually it doesn't matter about the, so the time increase is still linearly. Yeah, we can cut the huge, for example, we can cut a huge volume into very small tiles, and we can calculate it parallelly. Yeah.
Thank you.
All right, great. Let's thank our speakers. All right, our next paper is Fluid-Directed Rigid Body Control using Deep Reinforcement Learning, and Choi-Shung Pan will be presenting.
Thanks for the introduction. So I'll talk about our recent work on fluid control, and this works in collaboration with the Nankai University and the University of Maryland at College Park. So this figure illustrates a typical problem under consideration. Let's say we have 2 players, each controlling a fluid spout that can shoot incompressible liquid at the ideal rigid body. So we want to solve a control problem. The goal of this control problem is to push the ball to the other side. So let's say if the ball hit any boundary point on the left side of the screen, then player B will gain 1 point and player A will lose 1 point, and vice versa. Our goal is to generate this kind of animation, so we want to design a controller that controls fluid spout to gain as many points as possible. So more generally, we want to design a controller that can push a rigid body to a target state using a fluid as an actuator. And this problem has many applications where you're in animation control, where your fluid is dominating the dynamics of your simulation domain. But there are 3 challenging issues in this problem. The first one is that you're now controlling a very high of dynamic system. Let's say you use a grid-based method to discretize your fluids, and you can easily go up to more than 10,000 degree of freedom in your dynamic system. And then a second challenge is called non-smoothness. So in this case, your dynamic system has a lot of collisions between fluid particles or fluid and rigid body. So in either of this case happens, you're introducing some non-continuous operator in your dynamic system. And it's known that controlling this kind of thing is very difficult. And the last challenge we call distant reward. This means that if you apply a control command at your current time step, then the effect of this control command can only be visible after many time steps. So in this case, to achieve effective control, you have to take into consideration a long trajectory, many time steps. So I'll first talk about some previous work leading to our method. First, we know that to model this coupled dynamic system is largely a solved problem. The state-of-the-art simulator can bring multiple dynamic model into a unified representation, but the simulation cost is still high. So let's say at least proportional to the number of degree of freedom. But controlling this coupled system is way more challenging. The existing method for fluid control can only provide myopic control of a single phase fluid, either smoke or liquid. And this myopic means that they take into consider a small number of time steps, which is not enough in our problem. And we also know this previous work in 2009 where people can control a massless particle immersed in your simulation domain, in this case a leaf in this smoke domain. And this control actually take a long trajectory, and they can control at real time. This is really remarkable work. But still we cannot control a rigid body with non-zero mass. And I also note that these previous work are backed by two main techniques, either model-based trajectory optimization or model-free heuristic control rule. So let's analyze how can we extend this method or apply this method to our control problem. If you want to use heuristic control rule, then the key component in this method is to predict the result of a control. This can be done if your dynamic system is fully actuated. In this case of keyframe-based control, you can apply control force at every point of your simulation domain. Then you can do this. But in our case, we can only control the fluid spout that lie to the bottom boundary of a simulation domain, and most of the remaining domain is not controllable. So in this case, we can generate very plausible simulation because most of the domain satisfy your physical rule exactly. But it's not easy to predict the result without running a actual fluid simulation. If you perform such a prediction by actually running a fluid simulation, then the main benefit of heuristic control rule is lost because this method is supposed to be efficient. Or if you want to use trajectory optimization, then the main obstacle here is that they only work for a smooth dynamic system. Well, this is not the case in our problem where there are so many collisions, and if that happens, you cannot bring your gradient information across these non-differentiable operators. So at least it cannot be directly applied here. In this work, we want to propose a third alternative method of control based on deep reinforcement learning. And the idea is very simple. We just represent our controller using a deep neural net. The networks should be responsible for state estimation and control policy representation. The main benefit of using a deep neural net parameterization of your controller is that we can encode nonlinear and complex control skills will still be differentiable. And these neural nets are trained in end-to-end manner using deep reinforcement learning. And finally, we can generate real-time 2D controlled fluid animations at real time. So DRL can be considered as a stochastic variant of trajectory optimization that models uncertainty in both in your controller and dynamic system. The main benefit of modeling this uncertainty is that we can assume our dynamic system and controller are as a black box. We can apply a very general assumption on the dynamic system, such as your dynamic system is nonlinear, non-smooth, that's okay. And previously, the DRL has been widely used to control load of dynamic systems, such as this articulated rigid body, and we extended it to handle height-off system. So let's go deeper into the method, and I'll talk about some key components. So starting from how we model our dynamic system, this is very bookkeeping. We just use an incompressible NS equation for the liquid part and the Newton-Euler's equation for rigid bodies. Finally, the boundary condition is achieved by using the pressure force and the continuity condition of the velocity field. And we also add this last condition, which says that our pressure should be larger than 0 in this boundary region. This means that after your fluid and rigid body collide, they can still separate. So in our experience, this last condition provides much better plausibility. It's actually easier for our controller to achieve its control because you do not want the rigid body and the fluid to be sticky and they move all together, and this can be really nonlinear. So if they can separate, then rigid bodies sometimes can keep free flying, so it's easier for the controller to achieve the goal. And we discretize this bunch of equations using a hybrid of grid and particles. And we also use adaptive grid that provide higher resolution around the rigid body. This, in our experience, provide up to 4 times speed up in the training stage. And finally, we solve for positive pressures using this large-scale pressure solver in this previous work. And these components combined provide us with a well-defined dynamic system that bring your current state and action or control signal to the next state. Given this well-defined dynamic system, DRL formulated the control problem as a Markov decision process. So I very briefly covered the background. So MDP assumes that you start from your state 0, and you have a controller that can provide you with the action 0. That state and action, combined will grant you a reward 0. That's your initial reward. And you then invoke your dynamic system to move forward to your next state 1, and you do this again and again until you sample long trajectory. So the goal of control in this case is to maximize the cumulative reward. This is an expected reward because your controller is not deterministic. It's a stochastic controller parameterized by this vector W. So the problem of controller design or controller optimization is the maximization with respect to these parameters. Next, let's look at how we represent our controller. So this controller is a concatenation of two networks. The state estimation net that maps from the height of state of fluid to the load of features. And we introduce this block to greatly reduce the number of parameters in the neural net to be optimized. Let's say you use convolution layers and you can reduce the number of parameters. And the next network maps from the load of feature to the control signal. So the input to our state estimation net involve a liquid velocity field that encode all the information for all the liquid particles. And we also add a liquid region mask that mark the region occupied by your liquid. And the output is just 128 dimensional features. This network is a fully convolutional net, just a stack of different convolution layers. And we find that this encoder part actually is enough to represent the complex control skills, but it's difficult to train due to overfitting, because in a typical DRL training, the number of training samples you can experience in this training process only covers a very small subset of the entire state space. This can result in overfitting. So we can alleviate this problem by introducing a decoder, and this gives us an autoencoder, and we add this reconstruction condition which says that the encoder-decoder pair should reconstruct our velocity field. And we add this reconstruction loss to our reward function. So then the control policy net just maps the liquid velocity field and other minor features such as the position and the velocity of our rigid body to the desired control signal that involve the desired position, tilt angle, and emitting condition for our fluid spout. And finally, we add some Gaussian noise. By doing so, we satisfy the requirement of DRL that our controller should be stochastic. Now we can move on to the deep reinforcement learning part. So this involves two sub-steps. First, we want to use importance sampling to approximate this expectation. To do this, you start from initial state 0, and you have a stochastic controller that you can draw 3 possible actions, A, B, and C, from your controller. And from each action, let's say A, you sample a long trajectory to get the total reward A. This is the first sub-step. Then you want to optimize objective. And for this, we use this previous work and optimize a so-called surrogate objective. This objective is the probability for the controller to generate action A, B, and C weighted by the total reward. So this is very intuitive. Let's say if you observe from action A, your reward you have a higher reward compared with the other 2 trajectories, and you say that the controller should generate action A with higher probability. So this previous work says that if you control your step size in optimization very carefully, then optimizing the surrogate objective will bring you to the local maxima of the original objective. And we go to this complexity because the original objective is not tractable to compute. And this surrogate objective is very easy to compute. So we have covered all the main components of our system, and we just briefly introduced our algorithm. So each iteration of the algorithm involves 2 steps. The first step is one iteration of DRL training, and in this process, you also collect a lot of samples to approximate your expectation. And then you use these samples to update your autoencoder. At runtime, you just use the encoder part. Results. So you can see that our method, although it can solve a lot of control problems, each control problem is specified by a reward function that is specified by user. This can be a heavy burden on user side because you have to do a lot of fine-tuning of weightings. We can alleviate this by using automatic search on a cluster. So we allow users to specify a search range and step size for every weighting, and we assign different set of weightings on the master node, and each slave node should run an independent DRL using a specific weighting, and after everyone has converged, we just pick the best one. So the results in this paper generated in this way. And this figure shows the convergence history of 4 benchmarks in our paper, and on average, it converged within 500 iterations. In each iteration, we sample 32 trajectories each with 1,000 time steps. So altogether, this requires 16 million cores to your fluid simulator, and takes about 10 hours on our cluster, a Google Cloud cluster. So I also show the necessity of introducing this decoder part. You can see that on convergence, we can achieve significantly higher average reward by using this reconstruction loss. Next, I will show some animations by changing the reward function. We can keep this ball in the target position, and the actuator is the liquid spout. The training time is about 2.5 hours on the cluster. The method is also versatile, and we can change the rigid body shape and the type of spout. But in this case, the simulation cost for smoke is higher, so it takes a longer time. It takes about more than 10 hours on the Google Cloud. You can also generate this rotating cross by controlling the target velocity in addition to the target position. So the first three examples here are the single task, single agent control. We can also extend the method to multi-agent control. This is done by introducing two controllers with different parameters. And the unified reward function, we want the first player to minimize it and second player to maximize it. This generates a competitive ball game here. You have just seen it. The training time is still 3 hours. And the reward is the time of win for the player on the left. So this is compatible with the reward for two players. The left player should maximize it, right player should minimize it. We can also do multi-task control. In this case, you still have one controller, but you want to satisfy a set of different goals. And the goal is treated as an additional input to our control network. So in this example, I will show you a single fluid spout pushing a ball to hit different target positions on the ceiling. And the target position is this additional information. At test time, we draw a long list of target hitting points from a musical script. And you can see that in this long animation, our controller is very accurate. It doesn't make any error. The training time for this big example is 16 hours on a Google Cloud machine. So main limitation of our method is that it's very computational costly. You can see it's not easy to extend it to full 3D fluid dynamics, but still we can generate pseudo 3D animation. Here the fluid is modeled as a heat field and the dynamics using shallow water equation. This controller is still multitask. We can change the target position using the target position is the green block here. So for all this multitask training, in the training stage, you have to use multiple examples. You need to tell the neural net how to push your target to different positions. So this is why this kind of training is so costly. So conclusions. In this work, we present a new kind of control problem, the control of a hybrid system of fluid and rigid body, which is both high dimensional and non-smooth. And the main idea is to use a DRL, which can model uncertainty and also allow non-smooth dynamic system. And we do this by representing the controller using a state estimation and the control policy network that is trained in an end-to-end manner. After that, we can generate 2D and pseudo 2D animation in real time. So the main limitation, again, is still the high computational cost. So a brute force extension to 3D case is not possible. You can alleviate this problem by using a more sampling efficient DRL algorithm. There are a couple of this kind of algorithm proposed recently. You can also use a better simulator such as GPU-based simulator. But this doesn't change the complexity of problem. So in the future, we want to explore 3 directions. First, we want to try a dimension-reduced fluid model. This can probably provide 2 order of magnitude speed up. Maybe we can use it to extend to 3D animations. And we are also considering multiple interacting rigid body control. The final direction is called a fluid agnostic scale transfer. This means that we want to train a controller for a certain kind of fluid simulator and extend the scale to other simulators such as particle-based simulator, LBM-based method without retraining from scratch. Thank you.
All right, we have time for some questions.
Hi, I'm John Snyder from Microsoft Research. I'm wondering if you had done something simpler, like just discretize the control space and use more standard algorithms to just optimize that, and then let those kind of players play against yours that use your neural net. You know, do you get a much better player out of your algorithm than a simpler approach? Did you ever do an experiment like that?
Mm-hmm. I think that might work in many cases, but the main obstacle is that the number of state or grid cells will explode for complex scales.
But the state space of your controller could just discretize the state of the rigid body and what you're going to do now, like which direction you're pointing your fluid flow and whether you have it on or not.
Oh, you mean discretizing the state space instead of
the control space?
The control space.
Yeah.
Okay. Yes, I think that's interesting. I'm not sure, but I think it's worth trying, definitely.
Hi, Robert Britson from Autodesk. Sorry, really silly question, but in the paper you didn't have the citation for the large-scale pressure solver with the inequalities. I was just wondering, what was that paper?
It's like a large-scale quadratic programmer that can enforce the boundary condition for pressure being positive.
Yeah. So what is that paper? Or
that is a SIGGRAPH Asia 2013 paper.
SIGGRAPH Asia?
Yes.
Oh, okay, thanks.
Hi, I'm He from Leeds University. First of all, wonderful piece of work. And I might be wrong, but in your first example, it looks like there's a big variance on the control. I wonder if that has to do anything with, for example, possible lack of regularization on policy?
You mean a big variance in the control signals?
Yes. I mean, to keep the ball there in the air, the nozzle doesn't have to move with that big, within that big area, right?
Right, I understand. We didn't.
I might be wrong, yeah.
No, I think you're correct. But it's a hard question. I cannot say clearly which term is contributing to this effect or artifact. Yes, you're right. It just should keep in the center of this domain.
That's okay. Yeah,
yes.
All right, let's thank our speaker again. All right, the final talk of this session is automatically distributing Eulerian and hybrid fluid simulations in the cloud. And the talk will be by Philip Levis.
Great, thanks. Thanks everyone for making this session. This talk's going to be a little different than the previous ones. This is about a large-scale distributed system, so it's going to be about some low-level systems details. So I apologize now and thank you for your patience. So this work was really motivated by the observation that computation, especially large-scale computations, have moved to the cloud. By that I mean they can run on thousands of nodes in which you use commodity parts, failures are common, nodes straggle. And this is part of just a larger trend in the design of computer systems over the past 30 years. Right? Today we don't buy a 50 terabyte disk, we buy 101 terabyte disks and build a RAID array. Similarly, when you build a switching structure in a data center, you don't buy huge, powerful switches. You buy lots of commodity 10 gigabit switches and then produce something like the Jupyter fabric. And this notion of building big, complex, powerful systems out of small, sort of cheap parts has real implications. In the sort of the seminal MapReduce paper that really sort of laid the groundwork for modern data analytics, in one experiment on 1,800 hosts, 1,600 of them failed. So these are the kind of things you have to deal with. But in contrast, kind of simulations, fluid simulations today are kind of, twins and stuck in the 1990s. When we do a fluid simulation today, what do? We buy a really big machine, we put in lots of RAM, maybe, we run it on a GPU, or maybe if we're really crazy, we get a small high-performance cluster in which we then have to build the whole software stack from top to bottom. And this disconnect is in part due to the fact that running software in the cloud is hard. actually using these large distributed systems of commodity parts has a lot of systems challenges. Particularly, your application needs to handle dynamically scheduling away from slow nodes, fault tolerance, consistency across all the different nodes. The way we've done this in data analytics is with new platforms, things like Spark or Hadoop, that provide a new programming interface to you, some new API, which can hide all the systems complexity underneath and then allow you to write your high-level program. We can't really do that for fluid simulations because we have our existing simulation libraries. We want to use these existing libraries that we have. We can't just rewrite everything in some brand new framework. We don't particularly want to. And so that brings me to the title of this paper and this work. And so I'll just kind of walk through it bit by bit. So I'm going to talk about a software system called Nimbus, which allows you with a little bit of glue code to take your existing single-threaded fluid simulation and scale it out to run on many machines and hundreds of cores. You can do this for simulations of an underlying Eulerian representation, including stuff like particle level set, flip, and APIC, but you can't really do it for something that's purely Lagrangian or cloth. And it does this on cloud-based nodes, so nodes where you can have performance variations, cross-traffic in your network switching fabric, node failures, and all the kinds of nitty-gritty systems complexities that occur, and it handles all that for you. And the key idea to this, and the key way it does this, is it basically takes your large simulation and just breaks it into lots of little small simulations, as you'd expect. Each of these runs is just a single-thread simulation in your simulation library, and then under the covers, in between simulation steps, or in between operations, Nimbus automatically stitches all of these simulations, all of these sub-simulations together into one large aggregate simulation, updating ghost cells and doing all of that. And now to manage all the system complexity, uses the standard technique from cloud systems. There's a centralized controller that manages the whole computation, describes or decides which workers execute which parts of the computation, when data is copied, where data is copied, when to recover from faults, etc. If you use Nimbus, basically what this allows you to do is run bigger simulations faster. So here's just a 152 cube Fizzbam water simulation of water pouring into a glass. If you run it on a single core, it takes 335 minutes. If you use Nimbus, you can take that same simulation and run it on 64 cores. And this means you can run a 256 cube simulation in less time, in 268 minutes. So now I'm going to talk a bit about Nimbus's programming data and system models to give you a sense as to how this distributed system works to be able to execute your simulation library. So we start with this idea we want to, say, just advect velocity over, let's just say, a 1D simulation. Let's make it 1D for visual simplicity. So the one thing Nimbus asks you to do when you're writing your simulation is actually state what partitioning you want. How do you want to break this simulation up? And so you take your just advect velocity to, I want to advect velocity over these geometric bounding boxes. You represent your partitioning in terms of the geometry of the domain. So for example, I want to advect on the left and I want to advect on the right. I'm going to split this simulation into two. Then Nimbus takes that representation and does a lot of magic under the hoods, which I'll talk about, and turns this into two sub-simulations, one on the left, one on the right, which it then stitches together at runtime, such that it does the automatic transfers, and those two simulations are consistent. And the one bit of glue code you have to write to get your simulation library to work with Nimbus, there's two pieces. One is allowing Nimbus to be able to invoke your simulation operations. So that notion of like apply advect, well, you need to tell Nimbus how to do that. So a little bit of glue code there. Then a little bit of glue code that allows Nimbus to copy data in and out of your simulation data types. I'll talk a bit about more of this later, but Nimbus has to represent data differently, and so it needs to be able to move data between these two representations. As you put that together, this figure kind of shows the whole architecture of what Nimbus is doing. The key mechanism in the system is this 4-layer data model. So up at the top, as I show when you write your simulation loop, you describe what computations you want to do in terms of the geometric domain. So for example, I want to advect on the left, I want to advect on the right. This is then fed to a system component called the launcher, which transforms these geometric descriptions into a set of logical data objects. Logical data objects partition a variable disjointly over the domain. So these 4 bounding boxes are turned into 4 objects. A, B, C, and D, where A and D are center regions and B and C are ghost regions. This logical representation is then sent to the centralized controller, which actually binds those logical objects to particular physical objects, so memory in nodes on worker nodes. And so in this case, you'll have 2 copies of each of the 2 ghost regions, and so this becomes physical objects 1, 2, 3 on the left node, and 4, 5, 6 on the right node. Then on the worker translates these physical objects into the data representation that the simulation library expects, the application representation. And then you run your 2 simulations in parallel, and they're stitched together with the ghost transfers as needed. So if you think about the overall system architecture, the way this works is you have your driver program in the geometric representation that generates a logical representation, which is sent to the central controller. The controller then transforms that into the physical representation, which is sent to the worker nodes, which then translate that into your simulation library's representation. So the first challenge that comes up in building this distributed system is data representation. Simply put, the distributed system, in order to manage consistency, sees the world in terms of these logical and physical objects. But the application library sees the world in terms of these application objects, and the 2 are not the same. Often an application object, or almost always, consists of many physical objects. And the challenge here is both the distributed system and the application want these objects to be contiguous in memory, either for network transfers or just for as the simulation library expects. And so you have this challenge where they're expecting different layouts in memory, and you somehow need to resolve those 2 and translate between them. And so Nimbus has a system called the translator cache, which does exactly this. Essentially, it maintains consistency between the application and physical object representations. One simple option is just keep copies of both. This is very inefficient. You don't want to have huge copies of the center region since they're not usually copied unless you, between nodes, unless you're doing some kind of data migration. And so it sort of introduces 100% memory overhead. That's no good. So what Nimbus does is a write back cache policy, and essentially, if a physical object is ever older than its corresponding application object, you can free it. And then if you ever need a physical object in order to, say, copy a ghost cell, then it's regenerated on the fly. So the application representation is really the true data store, and then Nimbus copies things out as it needs using this little bit of glue code. This means in practice that just your ghost regions you have copies of them sometimes, and so you have less than a 10% memory overhead. The second problem is scalability. So in most systems that have a centralized controller to manage the computation, you can expect to execute at most about 10,000 tasks per second. And Nimbus is taking your program and converting it to this large task graph. Fluid simulations are computationally efficient for things like the reduction in your projection. You can easily execute hundreds of thousands of tasks per second, and so a centralized controller can't scale. And this means that the controller becomes a bottleneck for the computation. So here's a strong scaling experiment on a 3D heat diffusion example, where you can see as we scale up the number of nodes, kind of when we're running on about 8 or so workers, things are still faster, 4.5x speed up. But as we scale the number of workers, actually performance goes down, because what's happening is more and more tasks are being fed to the controller, and it just can't feed them out fast enough. And because we're doing strong scaling, the tasks are getting shorter, and so actually performance goes down. At some point, you only do 10,000 tasks a second, and if those tasks are being smaller and smaller pieces of work, the simulation slows down. So Nimbus solves this problem by actually caching the control traffic and the program structure. The key observation here is that fluid simulations are extremely iterative in nature. You're running a loop or nested loops that really execute the same set of operations in the same order on the same data objects. And so both the controller and worker nodes can cache large blocks of tasks in a structure called a template. And so a single control message can spawn, say, 1,000 tasks on a worker. Call it a template because it binds some values, like the physical objects that you access, but others remain free because they need to be determined at runtime, things like your task identifiers. So that's kind of a high-level view about how Nimbus works. Let's look at how well it works. So just to summarize, Nimbus is general, so it can support a wide range of Eulerian hybrid methods. You can port your production quality code, so something like a FizzBAM simulation, in about 2,000 lines of code. This allows you to run bigger, more detailed simulations faster. It can, in fact, scale past current simulation methods. I'll show that in a moment. So Nimbus is not the bottleneck, the simulation methods are. And furthermore, it can recover from faults and can reschedule computations for you. So that first claim, so we ported 3 different simulation libraries, 3 different simulations to 2 different libraries to work under Nimbus, FizzBAM, water, and smoke simulations. and then an open source heat diffusion simulation. So generally speaking, porting the library in FizzBAM, there are a lot of different data types, all of your different kinds of particles and stuff, about 20 or so. So it's about 1,500 lines of code to port the whole core FizzBAM fluid library. For the heat diffusion, it's 118 lines of code. And then the driver program, the actual thing you write for your simulation, for a FizzBAM water simulation, it's 620 lines. For smoke, it's 400. This is about equivalent to what a normal FizzBAM main control loop is like. For the heat diffusion, it's 94 lines. And once you do this, you put in these lines of code, then you can run bigger simulations faster on lots and lots of cores. It turns out the caches are pretty critical for this to perform well. So here's the same data I showed before, but now the x-axis goes up because we can go a lot faster. So this is scaling up. There's a strong scaling experiment on a 3D heat diffusion simulation. And so the bottom line shows what happens if you don't have either the translator or controller caches. And so essentially, the system bottlenecks at the controller, and it doesn't get faster as you scale out. If you introduce the controller cache, then we can continue to scale such that at 64 workers, we're running about 12 times faster. If we also include the translator cache, so doing the smart policies for write back, this performance increase goes up to 19.2x. So essentially, the cost of not having to copy those large center regions, adds about 72% performance. So one question you might ask is, wait, we have 64 times the nodes, but we only run 19.2 times faster. Why is that? What's the bottleneck? Is this Nimbus? Is this a simulation method? The answer is it's the simulation method, right? We have to do ghost cell exchanges. So what these experiments show is as you change the ghost cell bandwidth, how does the simulation scale? If you don't have to do data transfers, then you scale basically this almost with 1% of what the expected scale it is. That's the overhead that Nimbus introduces. As you increase the ghost cell bandwidth, you spend more and more time communicating. So data exchanges and not Nimbus are the bottleneck. Nimbus can manage system complexity for you. So here's one experiment where we took 64 cores, so 8 nodes, for a 256 cubed FizzBAM water simulation. 10 minutes into the simulation, we caused one node to slow down a lot, just synthetically, put a lot more computational load on it. If you don't have automatic load balancing, then the simulation slows down to the speed of the fastest nodes. That's the dotted line. It gets really, really slow. But using Nimbus, the controller can detect this and then automatically schedule computations away from that node and move them onto other nodes. It starts going a little slower because you're now putting a little more load on every node. Then at about 35 minutes, we caused one node to fail. So we just killed the node. So if you don't have automatic fault recovery, kind of your simulation stops. For any people who run simulations, you stop, go back to your state, and you have to manually restart it. Well, Nimbus does that automatically for you. It's periodically checkpointing based on its expected failure rate and then the cost of checkpoints and recovery. Detects the node failure, winds back, restores from the checkpoint, and just keeps on executing. So in summary, Nimbus is an open source software framework that allows you to take your existing fluid, Eulerian or hybrid fluid simulation, and parallelize it to run on hundreds of cores and lots of nodes in the cloud. It does a lot of the systems complexity for you, job management, rescheduling, checkpointing, all of that. And it's really designed for using with existing simulation libraries. You don't have to rewrite your whole simulation system. This allows you to run higher detail simulations faster. One interesting point here is if you look in the world of cloud computing, key value stores have really dominated that space for a very long time because of their very easy parallelization and distribution. But in contrast, right, the key idea here is to what allows Nimbus to do this translation all the way from your high-level loop down into these distributed simulations is this notion of geometry, the fact that you have a geometric domain, you can geometrically describe what these objects are, and that's just enough metadata for Nimbus to be able to do all of this management automatically for you. First, and it's also really, really concise. It doesn't require a lot of complex metadata. But as I've sort of shown, right now, if we want to distribute these simulations, the simulation methods, many of them aren't necessarily designed to scale out to hundreds of cores. And so to me, this creates this really interesting opportunity of now that we can distribute these things, maybe we need to come up with some new simulation methods that allow us to leverage this greater computational capability. So Nimbus is open source. You can download it. Encourage you to try it out, and reproduce any of the results from the paper. I didn't give all the exact experimental details, but they're in the paper. These are the students who did all the work. Unfortunately, immigration policies made them a little scared to come here, but Chinmay and Hong are looking for jobs, and they know lots about distributed systems and simulation methods. And I'm happy to take questions.
So we have plenty of time for questions.
Hello, I'm Jeff Late, Side Effects. It's very cool to see you build fault tolerance into this. I'm quite envious of that with our distribution. How big of the cells are you breaking into? Because usually with large time steps people want to do, we end up with a very large ghost bandwidth in our distribution. So I'm wondering how small the tiles are.
Oh, I mean, so that depends on, I mean, how much you want to distribute. So often 64 by 64 by 64 would be a common one, but you can do smaller. So one of the really interesting things about the cloud, and cloud networks in particular, stuff like an AWS, is that you have high delay but high bandwidth. So think you've got a 10 gigabit per second, full bisection bandwidth network. So what that means is that actually ghost cell sizes don't matter that much, because what you can do is you over-partition your simulation. So per core you have multiple partitions, and then you end up just pipelining, right, your transfers. Now when you get into barriers, right, like I need to do the global reduction, then you have a little bit of latency. But when you have 10 gigabit networks, but your minimum latency for a reasonable packet exchange is 100 microseconds, suddenly ghost cell sizes don't matter as much. And that's a real change from like the HPC world, where you have InfiniBand with 10 nanosecond latencies and 1 gigabit per second.
And so is this, what network is this over? Is this TCP/IP? How's it interconnected?
Yeah, this is just TCP/IP on top of, like on AWS.
So do you need to de-enangle for like the pressure projection to avoid the back slowing you down? That's what we found. We had one-way communication, so.
Interesting. So I'm pretty sure we disable Nagel's algorithm. Yeah, you don't want Nagel's algorithm. Right.
Hey, great talk. Craig Schrader, UC Riverside. How does the performance with Nimbus compare to the performance of just something like MPI?
Oh, great question. So
you got a slide for it.
The short answer is that effectively, when you get down to the actual execution of the program, et cetera, like it can match MPI. The challenge is that you have the central controller. And so the central controller can become a bottleneck in a way that MPI doesn't. And so if you really start pushing scalability out there, like you want to do a 1024 cubed FizzBAM simulation, which is, Ron tells me is the biggest anyone's ever tried, then suddenly you can start getting some overhead at the controller. But if you look at smaller scales, I mean, effectively the ability to pipeline things and all of that, like the data transfers are the same, the computation time is the same. And if anything, the fact that it can do the automatic scheduling means that you don't have to worry about managing all the complexity explicitly in MPI. So, but that's been our baseline really, is because, one of the things when you do this experiment is FizzBAM does have an MPI implementation, and so that's what we always have been measuring against in terms of performance.
Yeah, I was wondering about that. Thank you.
Yeah.
Hi, I'm Daniel Weber from Fraunhofer. Great talk, thank you. I was wondering, do you have to predefine the number of ghost cells, so the size of the halo? So I'm thinking about the advection algorithms which need to access different velocity fields, and I think it's not easily predictable on how far you need to access data outside of your region. So is this something you have to predefine and be conservative about that? Or
Yeah, so exactly. You have to know, like, exactly, given your CFL condition, what your time step will be, like, what's the ghost cell bandwidth? This is, to me, like, this is what simulations, when you have to do anything distributed, you do have to do that explicitly. And so when you define the partitioning over the domain, you define what are the size of my partitions and then what are the ghost cell bandwidths. And so you do that explicitly, yeah. And you do that per simulation, not for the library, right? So you, as I showed, like, here, let's change the ghost cell bandwidth from 0 to 3, right? And so.
Yeah, thanks. And maybe a related question to that, do you also reduce the memory consumption on your master node? So I would assume if you start the simulation, a large one, let's say 2048 cube, for example, then you might need a lot of memory on your master node and then it's distributed. Or do you have some splitting in mind where the overall memory consumption is reduced overall?
Yeah, the master, to think about it, it's maintaining metadata, right, about the status of objects and stuff like that. Generally speaking, compared to the actual simulation state, this is pretty small. Like even if I have a 2048, the master isn't tracking per cell state, it's just tracking per partition. And you can get millions of data objects in those cases, in particular for things like particle advections or if you need to do scratch regions. But that's usually, I mean, you've got some 10 gigabytes or something on this node. It's totally manageable. But I think you're right that more so than the size of this simulation in terms of the 2048 cubed, it has to do with how many partitions you have and how many objects you have. That's the limiting factor. So at some point, yeah, you can't scale down that each partition is a cell, because then you would have to maintain all this huge amount of metadata on the central controller. Absolutely.
Thanks a lot.
So unfortunately, it's 10:30 now. So all the speakers will be up front if you want to ask some questions. But let's thank them all again, and thank you all for coming.
Hey, John. I'm here, if you were worrying.
No, I saw you over there.
This is going to be
Only saw